Okay, everyone, this is homework problem number 7, which is Think and Solve 16.36. Here is a block of granite. The problem basically says deep in the earth, granite and other rocks are radioactive. This radioactivity produces heat. The heat that's produced does stuff like keeps the interior of the earth molten, heats up lava, and provides warmth to natural hot springs. So we need to look at a chunk of granite like the one you see right here. We need to ask ourselves, after 13.5 million years, what is the temperature change of this chunk of granite? In other words, what is delta T for this chunk of granite? The hint says to use the equation Q equals mc delta T, which I will, and now my next task is to isolate delta T. That's the $ variable. So if Q equals mc delta T, I'm going to divide through by mc. And now I have to ask myself, what do I know and what don't I know? Do I know Q? No. Do I know M? No. Do I know C? Yes. So now I'm stuck, so I'll go back to reading the question again and see if I can get any clues this time. This sentence seems interesting. This is due to the average release of about 0.03 joules per kilogram each year. I'm going to write that down, 0.03 joules per kilogram per year. So I'm getting 0.03 joules per kilogram each year for 13.5 million years. You can see that years in the denominator cancels with years in the numerator. So now what I'm left with is the number 0.03 times 13.5 times 10 to the 6th. The units I'm left with are joules per kilogram. The problem is basically asking you this: if 0.03 joules of heat is spit out per kilogram of granite each year and you wait for 13.5 million years, what is the increase in temperature for that 1 kilogram of granite? Okay, if I go back to step number 2, I don't know Q and I don't know M, but maybe I do, because in step 4, I actually have joules per kilogram. And what is a joule? A joule is heat, Q. And what is a kilogram? A kilogram is mass, M. So there's Q over M. So now I can update line number 2. Q over M is this number, 0.03 times 13.5 times 10 to the 6th. The units are, again, joules per kilogram. That is Q over M. And now I'm going to divide Q over M by C. And C, in my case, is 800 joules per kilogram Celsius degree. Let me just reiterate. In statement number 2, I didn't know Q, I didn't know M, but I did know C. Doing steps 3 and 4 actually spit out that Q over M fraction. This is Q over M. Going back to number 2, this is C. So this is a way to get Q over M, which I then divide by C to finally end up with delta T, which is my $ variable. When I do dimensional analysis, I hope to end up with Celsius degrees. Not degrees Celsius, but Celsius degrees, because that is delta T. I'm going to multiply what I have in number 5 by the number 1. And here's how I'm going to write the number 1. The numerator needs to equal the denominator, so there you have it. My numerator is the same as my denominator. That's the number 1. And now I can do some canceling. Joule cancels with joule. Kilogram cancels kilogram. Celsius degree cancels with Celsius degree. Upstairs in the numerator, kilogram cancels with kilogram. Joule cancels with joules. And I am left with Celsius degree, which I was hoping to end up with. That's it. So my last statement here is 0.03 times 13.5 times 10 to the 6th over 800 gives me a number. In my case, it's 506.25, and the units are Celsius degrees. Mastering physics might round to 510 Celsius degrees.